Hello, my name's Thanom. I'm from UNSW. Today I'm working through some of the MATH1011 calculus problems from the section 2.3 rules of differentiation. So we're just going to differentiate a variety of functions here, starting with 2a. We're asked to find d dx of this, so differentiate this expression here. This is a product, it's a product of x squared plus x and x cubed minus 1, except I don't really want to use the product rule because it will probably be easier for me to simply simplify the expression and expand it. So I'm not using the product rule for this particular question. I'm just going to simplify this here. If I expand, I get x to the 5 minus x squared plus an x to the 4 minus an x. So they're exactly the same expression, and so now I can differentiate that. I'm actually differentiating, so I don't need to say I'm going to calculate d dx of it. To differentiate x to the 5, I'm going to bring down the power and reduce the power by 1, knock 1 off the power, minus, bring down the power, 2, knock 1 off the power gives us x to the 1, x squared differentiates to 2x there. Plus x to the 4 differentiates to 4x cubed, and minus x, we're going to differentiate to minus 1. So this is the derivative of x squared plus x times x cubed minus 1. Much easier to expand first and then differentiate rather than use a product rule. So for part E here, we do have a quotient. We have x squared plus 2 square root x, all divided by x cubed. But again, I don't need you to use the quotient rule here. I could just simplify the expression inside the brackets there. So x squared divided by x cubed, that's just 1 over x, okay? Or x to the minus 1. Plus 2, this is x to the half divided by x cubed. X to the half divided by x cubed is x to the minus 2.5, or x to the minus 5 on 2, if we write that as an improper fraction there. So I just need to differentiate this expression. This is a power of x, so I need to just bring down the power, minus 1, and reduce the power by 1, takes us to minus 2 there. So x to the minus 1 differentiates to minus x to the minus 2, plus this multiplying constant 2 is just going to hang around there. X to the minus 5 on 2, I bring down the power and reduce the power by 1. Minus 5 on 2, subtract another 1, gives us minus 7 on 2, or minus 3.5 there. So those 2's cancel here. Let's just rewrite this a bit neater. Minus x to the minus 2 is the same as minus 1 on x squared. The 2's cancel, so I'm going to subtract 5 over, right, the 5's there, but x to the minus 7 on 2 is 1 on x to the 7 on 2. So that's 1 on x to the 7 on 2 here. And you could leave it like that if you want. You could write this as 3.5. You could write it as an x cubed times the square root of x. All these are correct ways to write this derivative here. But the key is that we simplify this expression first before we differentiate the expression. Moving on to 2f. We have a quotient here, 3 minus x on x squared minus 3. We can't easily simplify that, so we're going to use the quotient rule there. So for our quotient rule, we're going to let f be the numerator and g be the denominator here. So f is going to be 3 minus x, g is going to be x squared minus 3. So f dash, 3 minus x, 3 differentiates to 0, minus x differentiates to minus 1, and g dash, x squared differentiates to 2x, subtract 3, minus 3, that's going to differentiate to 0 there. So these are our expressions for f, g, f dash, and g dash, and our quotient rule says that f over g differentiates to f dash g minus f g dash over g squared. So that's our quotient rule there. So substituting in the correct expressions, we have f dash g, so that's minus 1 times x squared minus 3. Subtract f g dash, so 3 minus x times g dash, which is 2x, over g squared, well that's just x squared minus 3 all squared. Now we can just neaten up the numerator. So on the numerator we have minus x squared plus a 3 minus 6x, and then this is going to be plus 2x squared on x squared minus 3 all squared. Minus an x squared plus an x squared is just x squared minus 6x plus 3 over x squared minus 3 all squared. I can't easily factorize the numerator. I will just leave the derivative like this. So this is the quotient rule here. F over g differentiates to f dash g minus fg dash over g squared. You just need to be careful to get all your derivatives right and to get your algebra right here. Moving on to 2g, we're differentiating x squared e to the minus x. This is definitely a product. We will need to use a product rule. So f is the function x squared, say, and g is the function e to the minus x. So f dash is 2x, g dash, e to the minus x, well e to the anything will just differentiate to the same thing. E to the minus x differentiates to e to the minus x. But the chain rule says I need to multiply by minus 1. Multiply by this inside differentiated here. So that's minus e to the minus x, if you like. So our product rule is differentiate the first, keep the second, plus keep the first, differentiate the second, f dash g plus fg dash. So substituting these in here, we're going to get 2x times e to the minus x, f dash g, plus fg dash is x squared times minus e to the x. So neatening this up, 2x e to the x minus x squared e to the minus x. If you want, I guess you could factorize e to the minus x e to the minus x out and be left with 2 minus x in the brackets there, and that looks slightly neater. So we have a quotient rule here and a product rule here for a couple of functions. In 3g here we have a composite function. We have inverse sine of x on 3. So there are layers here. So if we want to differentiate inverse sine, our main rule for differentiating inverse sine is inverse sine of stuff differentiates to 1 on the square root of 1 minus stuff squared. That's our rule for inverse sine. This happens to be x on 3 in here. The chain rule says in addition to that we need to multiply by this inside function differentiated. X on 3 differentiates to 1 on 3, or if you like, x on 3 is 1/3 x, so that differentiates to 1/3. So here I have 1 on the square root of 1 minus x squared on 9, and we're multiplying that by 1/3. Couple of ways you can do this. You might like to make a common denominator here of 9, or you might like to think of 3 as the square root of 9 and put that inside that square root. I think I'll do it that way, but there's lots of ways to do it. So on the denominator here, we really have the square root of 1 minus x squared on 9 multiplied by 3 squared, or multiplied by 9 inside that square root. So 3 is the square root of 9. So then we can see, once we expand this 9 in, we have 9 minus x squared. So inverse sine of x on 3 differentiates to 1 on the square root of 9 minus x squared there. Now we need to differentiate tan squared x. It's written like that, tan squared x, but I'm going to rewrite it as tan of x all squared, which is what it really is. This is just saving on brackets. The reason I want to write it like this is because then I can see the 2 layers of my function. On the outside it's something squared. On the inside it's tan of x. So we're using the chain rule here. The outside function, something squared, differentiates to 2 times something to the 1, right? So we bring down the power, reduce the power by 1. That's what the outside function says. The chain rule says in addition to everything else, multiply by the inside function differentiated, multiplied by the derivative of tan x. So here we have 2 tan x multiplied by tan differentiates to sec squared x. So here our tan squared x will differentiate to 2 tan x sec squared x there. We have another composite function here, this time a log of a log. So our chain rule says differentiate the outside function. Log of anything differentiates to 1 over that. So log of log x differentiates to 1 over log x. That's the outside function. The chain rule says in addition multiply by this inside differentiated. The inside here is log of x here. So we need to multiply by log x differentiated. So we get 1 on log x multiplied by log x differentiates to 1 on x. So simplified, this looks like a 1 on x log x there. So you have to keep track of which functions are on the outside and the chain rule which says multiply by that inside function differentiated.